Good morning, ladies and gentlemen. I'm Chaoming Fang, a junior student from Beihang University, China. It is my pleasure to introduce my work, Flaps 2029, at the lecture section of Emerging Applications. The title of my report is Utilizing Wearable GRF and EMG Sensing System and Machine Learning Algorithms to Enable Locomotion Mode Recognition for In-Home Rehabilitation. My report is organized in 5 parts, including background, innovation, sensing system design, recognition algorithm design, and results and discussions. Physical rehabilitation training is an important way to help people suffering from lower limb disability to regain mobility. During the process, it is of great significance to monitor the physical information, such as gait and muscle condition. Traditionally, the scenarios to obtain this data are mainly located in hospital or therapy institutions. However, there will always be some situations that bring a lot of inconvenience to patients going to the hospital for rehabilitation training. For example, the COVID-19 outbreak keeps everyone staying at home, and patients going to the hospitals will face higher risks of the infection of the virus. Besides, patients may feel pressure when being monitored, resulting in low-quality data, and conversely influencing the evaluation of the rehabilitation effect. Considering all these situations and demands, it would have been nice to allow the patients to conduct the training at home and send their physical information to the doctors in the remote end. And this is the so-called in-home rehabilitation. With the help of the fast development of the wearable devices and the Internet of Health Things, this rehabilitation approach is gaining popularity not only for its convenience, but for its great potential in collecting high volumes of useful data by conducting long-term monitoring. For in-home rehabilitation, locomotion mode recognition is important. Locomotion mode means that when human being faces different environmental scenes like stairs, ramp, or obstacle, the brain will automatically coordinate to your limbs to adapt to these environments. It is proven that conducting rehabilitation training under different locomotion modes is beneficial for the patients to regain most of the mobility, and therefore, under the scenarios of in-home rehabilitation, the locomotion modes are closely related to the interpretation of body signals picked up by wearable systems and must have information delivered to the hospital under an IoHT architecture. However, the successful broad use of locomotion mode recognition for in-home rehabilitation has not been reported yet. A possible explanation is that, generally, a rather complex sensing system with many sensors is required, but the utilization of multiple sensors not only increases the overall component cost, circuitry complexity, and energy consumption, which are undesirable factors for electronic products, but also brings users inconvenience when used. The purpose of this work is to achieve both the simplicity and the accuracy in the locomotion mode recognition system. Specifically, there are 2 innovations in this work. Firstly, we smartly designed the multisensory strategies and carefully selected the measurement locations so that the sensing information compensate for each other. Secondly, we extracted highly correlated features with obvious physiological significance for the machine learning algorithm, and we will explain our methodology in detail. But firstly, we designed the experiment protocols to collect the dataset. We predefined 5 locomotion modes, including level walking, ramp ascent, ramp descent, stairs ascent, and stairs descent. The ramp was angled at 10 degrees, and the stair height was 10 centimeters. We recruited 10 healthy subjects, including 6 male and 4 female, to conduct the 5 locomotion modes repeatedly. Ultimately, They produced 3,573,241 observations with 2,707 strides in total. Next, the sensing strategy is presented. We choose to integrate the EMG signals with GRF signals. We present the schematic diagram of our applied sensing structure in the figure. We detect the EMG of two muscles of the leg. They are tibialis anterior and soleus. Meanwhile, we detect the GRF of the hallux and heel. The sensory applied are all flexible. We use the AGCL bipolar electrodes with gel to collect the EMG signals and force sensitive resistors, the FSRs, to detect the GRF signals. The detailed parameters of our applied sensors, and including the size, the electrical attributes, the measure range, are demonstrated in the table. And then we design the readout circuitry and the transmission circuitry, and they are conceptually depicted in the figure. The readout of the EMG and GRF signals are parallel. The raw EMG was amplified by differential amplifiers to suppress the common mode input, and ADC and bandpass digital filtering was followed by the embedded MCU. For GRF signals, the resistance change of the FSR was linearly converted to a voltage change by a proportional operational amplifier and then converted to a digital signal by an ADC. Both the digital AMG and GRF signals were then conveyed to two Bluetooth devices by the serial protocol and transmitted wirelessly via Bluetooth to PC. And after the EMG and GRF signals are collected by the sensing system, a series of the procedures should be applied to distinguish different modes. The approach we designed can be summarized in the figure. Firstly, we pre-process the raw data. Normalization is performed to reduce the variability of each stride and segment it into each stride. Secondly, we extracted features from each stride. Here, we innovate the convention feature extraction technique, and we propose the biomechanical features. This is because the EMG and GRF signals of the lower limb is typically similar in each stride, and they follow the principle of the biomechanics. Therefore, we can observe the experiment results and refer to the research of the biomechanics, and totally, 21 biomechanical features are selected. Finally, the extracted features were used to train the machine learning algorithm, IEEE, and the SVM model, and then the model was used to predict the locomotion mode. A tenfold cross-validation was used to evaluate the accuracy of the trained model. Now we present the experiment results of this work. A typical profiles of the EMG amplitude and the normalized GRF stress values under different locomotion modes is demonstrated in the figure. We can infer that there are differences between each mode in the profile we present here, and in fact, that this difference can be explained in biomechanics as we stated. For example, when we're walking on the level ground, the main activity of the soleus occur at about 50 to 60% of the gait, and the heel will contact the ground prior to the hallux. And while at the stairs descent, the soleus is most active at about 10% of the stride, and conversely, the hallux contacts the ground first when walking downstairs. Well, this is because when you are going downstairs, you reach out your toe first naturally to avoid losing your balance, and consequently, when the body weight goes to the toe, the soleus should contract to support your body. These different patterns can be reflected in the biomechanical features we extracted. And now we present the confusion matrix of the SVM model in the figure, and we reached an average accuracy and the variance of 96.38% and 1.08%. And we can infer from the figure that the model achieved the best recognition performance in recognizing the stairs descent, and with the highest accuracy of 99.64%. And however, the performance of distinguishing level walking from the ramp descent is relatively lower and less robust, with an error rate at 5.04% and a variance of 3.49%. The variance in the recognition accuracy can be solved by enlarging the volume of the training data. A comparison of our results with existing work is presented in the table, and it shows that our work reduced the total number of the sensors, and the fewer sensors that are applied, the less complex and energy-consuming the circuit structure needs to be in order to obtain and process the signals. Thus, our work resulted in reduced component costs, circuit complexity, and energy consumption, while reaching a very similar and even higher overall accuracy. And this potentially promotes the development of the locomotion mode-enabled in-home rehabilitation system. And finally, we depict the application of the system developed in this work under an IoHT architecture. The EMG and GRF information for people who need rehabilitation are detected and processed by front-end detectors. Then, the signals are analyzed and locomotion modes are recognized in end terminals, such as personal computers or smartphones. Finally, the integrated information is transmitted to remote end terminals. By monitoring changes in the locomotion modes and EMG and GRF of the user, further analysis can be applied for various purposes, such as disease diagnosis or rehabilitation guidance. The developed IoHT system enables related individuals or institutions to monitor medical data and evaluate therapy performance with the patient at home or in other daily scenarios, which potentially reduces the burdens of both the therapists and the patient and broadens the interaction methods in the rehabilitation field. This is the end of our report. Thanks for listening.